Welcome to video 73 in our series on tensor calculus. In this video, we're going to wrap up our study of the surface covariant derivative by reviewing its properties. Now that will include the properties that we have analyzed in the past couple of videos, where we've noted certain changes and modifications that we had to introduce, but I'm also going to go over the whole set of the properties that do not need to be modified. That is, that work exactly as they worked for the covariant derivative that we worked with back in video 28 and 32. So we're not going to derive anything new here, but we're simply going to review all the properties that relate to the surface covariant derivative. We'll start with the basic definitions. In videos 71 and 72, we discovered that there are four basic forms for the surface covariant derivative. We said that if our vector t lies in the tangent plane, then we can use these forms. But if the vector does not lie in the tangent plane, we have to use these. Now let me mention that these last two forms are universally applicable to any vectors, those that lie in the tangent plane or outside the tangent plane. So these we can use for any vector, but the first two can only be used if the vector lies in the tangent plane. We cannot represent a vector outside the tangent plane by using surface indexes, so that's what makes us use these forms here. Okay, now correspondingly there are four different ways to represent the partial derivative then, depending on which of the definitions is applicable. Again, these two are restricted to vectors that lie in the tangent plane, and these are universally applicable. Okay, now these forms look a lot like what we found in videos 28 and 32. The only real difference is the addition of these terms out here. We found that for a curved manifold, we have to add these terms, which represent a normal projection, in order to accommodate the fact that the result of our partial derivative here may not lie in the tangent plane. So we have to add this as a normal projection. Okay, now these definitions look very similar to what we derived as a normal covariant derivative back in videos 28 and 32. And as a result, almost all of the properties of that derivative continue to apply here. We've already gone over some exceptions, but there are a whole host of properties that continue to work, and that's what we really want to look at today. So let's start with what we found in video number 20. In video number 20, we discovered the sum rule. We found that the covariant derivative of a sum of tensors is equal to the sum of the covariant derivatives. And we can factor out scalar properties, scalar factors here. So that means that this operation of taking the covariant derivative is a linear operation. And I've given an example here where our tensors are mixed tensors. They have each has a surface index and an ambient index. So the only restriction in this is that the index structures throughout have to be consistent. And of course, that's a condition that was true back in video 20 as well. So the point here is that the analysis we did in video 20, if you were to repeat that for this example, you'd find that it works just fine. There's no restriction that the indexes have to be ambient indexes or that they have to be one type or the other. They can be ambient indexes, surface indexes, or any mixture of them as long as they're consistent throughout. Alright, well in videos 34 and 36 we discovered the product rule. The product rule being that the covariant derivative of a product of tensors is equal to the derivative of the first times the second plus the first times the derivative of the second. Now if you go back and look at that analysis, you'll see that there is again no restriction for the type of indexes. If you were to apply all the principles and analysis we did in these two videos to this form, you'd find that it works just fine. We're able to mix indexes in any form like this, and the product rule continues to apply. Now in videos 34 and 35, we were able to derive a process for finding the covariant derivative of a tensor of any rank. Well, if we apply that same process to the definitions for the surface covariant derivative, we come up with an expression like this. So we've got 4 different forms for the surface covariant derivative, so it makes sense that each of these 4 terms would roughly equate to each of the 4 different definitions. And that's because I have 4 different types of indexes here. Some in the upper position, some in the lower position, some are surface indexes, and some are ambient indexes. So let's walk our way through this just to make sure we understand it. First of all, as usual, we find the partial derivative of our object, and then we're going to form a contraction based upon each of the 4 indexes. So here we have a contraction of the I index, here we have a contraction of the J index, here we have a contraction of the alpha index, and this is a contraction using the beta index. Okay, now notice when the index is in the upper position, we have a positive term, and when the index is in the lower position, we have a negative term in each case. And when the index is a surface index, we simply use the surface Christoffel symbol as a factor. And when we have an ambient index, we use the combination of the ambient Christoffel symbol with the shift tensor. So that's exactly consistent with the 4 different definition types that we stated a moment ago. So with a little practice, you should be able to write out the surface covariant derivative of a tensor of any rank or mixture of indexes, and you should be able to do it simply by inspection. Now in video 34, we discovered that contracted indexes do not participate in this process. The process of finding a covariant derivative involves only the free indexes, and the same is true for the surface covariant derivative. So anytime we have a contraction of indexes like here or here, whether they're surface indexes or ambient indexes, then there are no extra terms out here because this is in effect a tensor of rank 0. Both of these are, so there are no extra terms. And we discovered that that means that the covariant derivative of a tensor of rank 0 is just the partial derivative. It has none of these extra terms. And that leads us to see that therefore the covariant derivative of a scalar function is just its partial derivative. So all of that is true for the surface covariant derivative. It's true for surface indexes and ambient indexes. In this last example down here, you can see that we have a contraction of I and a contraction of alpha. So beta is the only free index in this expression, and therefore we have only this one term. Okay. Well then, in videos 37 and 38, we explored the metronelic property. Now, here if you go back to videos 37 and 38 and look at the derivations we did for these objects, you'd find that they work equally well for these guys up here. There's nothing about those derivations that limit them to the ambient space, the ambient coordinates. That works just as well for the surface coordinates. However, in video 71, we found that this one was an exception. So what we can say is that the ambient basis vectors are metronelic with respect to our surface covariant derivative, but our surface basis vectors are not. So here we do not get zeros, we get non-zero values. Notice, however, as we pointed out during the discussion, that if our curvature tensor is 0, as in a plane, then we recover the metronelic property. So when the space is in fact Euclidean, then these values will be 0. At this point, let me remind you of a relationship we derived in video number 72, and that is the chain rule. We said that the surface covariant derivative is related to the normal covariant derivative by means of the shift tensor, as long as our tensor is expressed exclusively in terms of the ambient indexes. So this doesn't work if any of these indexes are surface indexes, but as long as all of them are ambient indexes, then we can make this association. So again, this operation is related to this operation by means of the shift tensor. In video 38, we defined the contravariant derivative, and we can do the same thing for the surface. So this is the definition of the surface contravariant derivative, and it's the same form we used back in video 38. Now, it works because the contravariant metric tensor here is metronylic with respect to the surface covariant derivative. So this can move in and out of the operation without altering the result of the operation. Now, this definition in turn leads us to the definition of the surface divergence. And we define this the same way we defined it back in videos 28 and 38. Here we're using a vector that we stipulate to lie in the tangent plane. And if it does, we can use these surface indexes like this to define the surface divergence. And of course, we can contract them in either direction. And that gives us a scalar value that applies strictly to the surface of our manifold. Okay, we do something similar with the gradient. We define the surface gradient using our surface basis here contracted with the surface covariant derivative of a scalar function. And that gives us a vector that lies in the tangent plane. And of course, we can contract it in either direction. And associated with our surface gradient, of course, is the surface directional derivative. So if we take the dot product of our surface gradient with a unit vector that lies in the tangent plane, then we're going to get the directional derivative along that particular path. Next, we have the surface Laplacian, defined exactly the same way we did back in video number 39. It's just the combination of these two operations contracted together. And it works exactly the same as it did back in video 39. And then finally, we can make use of the surface Voss-Weyl formula. And these formulas are exactly the same as we defined back in video 49, just using surface indexes. So we can use these forms to evaluate the divergence or the Laplacian for surface coordinates. Okay, with all that having been said, I'm sure you can appreciate the fact that the vast majority of what we did with Euclidean space carries over to curved manifolds. With just a few exceptions, the application of tensor calculus to a curved surface is almost identical to that of a plane. In fact, by generalizing the relationships, we're able to treat a plane as simply a special case of a curved surface. All right, I want to end the video by showing you what the gradient, divergence, and Laplacian look like in each of our sample surfaces. I'm not going to go through the actual calculations. The technique is something we've already demonstrated in videos 40 and 50, so if you need a refresher, you can always go back to those videos. We'll start first of all with the cylindrical surface, and what we have here is the gradient of the cylindrical surface. And this would be the divergence, and this would be the Laplacian. So again, if you need to see how these are calculated, just go back to videos 40 and 50. All right, moving on to the cylindrical surface, this would be the gradient. And then we'd have the divergence and the Laplacian. And finally, same thing for the torus. We have the gradient, the divergence, and the Laplacian. Again, if you need to see how this is done, just go back to videos 40 and 50. It's exactly the same technique that we'd use here.